When we talk about artificial neural network or artificial intelligence, for that matter, we're actually borrowing inspiration from the most powerful information processor that we know of, namely the human brain. Uh, but before we design artificial intelligence systems that mimic or interact with our biological systems, we need to first understand the fundamental of how the brain actually works and processes these information and these signals. And today we're going to talk about just that. We're going to talk about neurons, synapses, spikes, and so forth. And we will try to understand the mechanisms that give rise to our perception, the meaning, and the computation that goes within the natural systems, such as our biological brain. By exploring these mechanisms and how the brain encodes information as well as interprets these signals, we will try to lay the groundwork for designing more adaptive, more efficient, and more brain-inspired technologies such as artificial neural networks and neuromorphic computing. But before we start, let's first look at the things that we already know about the brain and the things that we are in the process of getting to know about the brain, as well as the things that we actually don't know much about yet, but we're still exploring. So the areas in which we have extensive scientific support for, as well as extensive research in both neuroscience and other sciences, is the following information. Neurons communicate via electrical spikes, as in action potential, as well as the electrical waves, as in brain waves, that happens between the neural networks within the brain. Synapses transmit these signals chemically, and their strength can change with the synaptic plasticity that we'll also talk later on today. Temporal and rate coding are both observed within the brain, things we'll also talk about. Neural representation emerge in layers from early sensory areas to higher cognition. Neurons integrate input over time and space and only fire in certain thresholds when those thresholds are met, as well as learning alters the synaptic ways that is based upon how we learn things during the short term as well as long term periods of time. That helps us to with the plasticity of the brain as well. Next, look at some of the widely accepted models and theories within the field of neuroscience. The first one is that the brain doesn't decode spikes as in neurons being turned off and on, like a fixed symbol system. It builds internal representations where this view reflects the current thinking in computational neuroscience, for example, as well as cognitive sciences. It contrasts the outdated the fact that the spike is a symbol metaphor. It's actually not believed that is a spike symbol metaphor, but that it's a decoding of the internal representations within the brain. Next, a single spike means nothing in isolation. So for example, when a neuron is off and on, just it being on and off, it means nothing. This is something that we thought of in the past, but now we know that that's not the case. It's a simplification to emphasize that context is very crucial. It aligns with known neuroscience, but it's a metaphor and is not a literal statement. Next is the fact that the brain creates meaning through layers of processing. This is consistent with how we understand visual as well as auditory cortex hierarchies. And lastly, representation instead of translation is what's important. This is supported by modern neuroscience and machine learning, especially in deep learning, where we build models with internal features that are the representations of something that we come to understand. And here are the things that we still do not know about the brain and the things that we're still exploring. We're still exploring the exact role of the timing, namely the temporal coding, versus the firing rate, namely the rate coding. Both are observed in the brain, but how much each of them contribute to different functions, it's still being studied. Next, we're still exploring whether spikes timing is used for symbolic-like computation or richer dynamics. Spiking neural networks, or SNNs, and neuromorphic systems are trying to mimic this phenomena, but the exact biological strategies are complex and still unfolding. And lastly, high-level meaning formation, like seeing a cat, for example, from low-level spikes. We have good models, but the detailed pathways in which the perception is formed and the perception becomes conscious recognitions are still not fully understood within the brain. How does the brain turn raw electrical signals and or spikes into meaning, into perception, into thought? To understand these, we need to go beyond the idea that the brain is a simple decoder of a signal. In truth, the brain doesn't translate spikes into labels like, for example, cat, or a sound, or a face. Instead, it builds meaning through a process of learning, pattern detection, and layered computation. This process happens across a vast, interconnected network of neurons. Each neuron is essentially a decision maker. It receives inputs from many other neurons through its synapses, where these inputs are electrical signals called spikes that are either exciting or inhibiting, meaning they are either ones or zeros. If the combined input exceeds a certain threshold, the neuron fires its own spike and passing the signals towards the next layer of neurons. But this isn't just a yes or a no relay system. The magic lies in the patterns where spikes arrive and they come from, where they come from, and then how many of these spikes arrive at once and how strong their impact is. Let's start at the level of one single neuron. You can think of that one neuron like a music critique, listening to an orchestra. It doesn't respond just to one note. Instead, it listens for a combination of instruments playing together in a particular rhythm or harmony. If the pattern sounds right, the critique gives a standing ovation and the neuron fires. If not, it stays silent and just like a critique taste evolves, a neuron's sensitivity to pattern changes over time. This is learning, which we also call the plasticity. One important way neuron encodes information is through the rate at which they fire. If a neuron receives a lot of strong input in a short amount of time, it may fire rapidly, signaling high activation. That's called the rate coding. But there's also temporal coding, which involves not just how often a neuron fires, but when the neuron fires relative to other neurons. A spike that arrives millisecond earlier or later can change the outcome of the meaning of that spike. Timing matters a lot within the brain. But even with these details that we just talked about, we still haven't answered the bigger question. How does this whole thing add up to a perception? Like, for example, us seeing a cat. We perceive seeing a cat, or hearing a melody, hearing a music, or recalling a memory. The key is in the networks of neurons, not the individual neurons per se. One spike on its own means very little to the perception in which we have, for example, of when we see a cat. But when thousands and thousands of neurons fire in coordination based on patterns that they have learned to recognize, the brain then enters a specific state in which we call it the perception. The brain is made up of very specialized regions and areas that work together in order to process these signals. The primary visual cortex processes, for example, edges or lines or simple shapes. Other areas of the brain, for example, handle more complex objects or even faces. The hippocampus, on the other hand, binds together experiences and supports memory formation. Each of these areas, when working together, these different layers of neurons and regions of the brain, they build together representation of hierarchy layer by layer. So for example, when you look at an image, light enters your eyes and hits the retina. The retina then has specialized neurons like photoreceptors that convert light into electrical signals. These signals then are passed through bipolar and ganglion cells, for example, where these cells fire spikes that travel down the optic nerve to the brain. That already at this stage, the signal is not just a raw image, but it's a pattern of activity emphasizing contrast, motion, as well as the edges. And once these signals reach the lateral part of the nucleus, for example, in the primary visual cortex, the brain begins detecting edges at specific orientation, where some neurons might only fire when they see a vertical edge, for example, and others respond to horizontal edges, for example. These neurons don't know what they are seeing, but they are very good at detecting pattern in space and light. As these signals progress onto higher visual areas, neurons become tuned to more complex combination. For example, they might respond to curves or corners or to textures or color patterns. And by the time you reach the specific part of the cortex of the brain, certain neurons fire only when they detect entire object like a face or a hand or a cat, for example. But there is the key idea that none of these neurons know what a cat is in any symbolic sense. They don't translate the pattern into the word cat, for example. Instead, through years of experience of seeing cats, for example, they have become wired to fire in a certain way when a cat-like pattern emerges that has the features that appear in the visual cortex and visual field of the brain as a cat. That firing pattern becomes our experiences of seeing a cat, as an example. And this is what we mean when we say an internal representation. The brain doesn't store the label cat in this example in one neuron. Instead, its distributed network of neurons across different areas collectively represent the catness of something that we see. Their coordinated firing brings the perception into our awareness. Meaning arises not because there is a decoder in our head, but because the pattern itself is meaningful, which leads to useful behavior, recognition, memory recall, and so forth. And so, how does the brain know whether a spike is important? It doesn't actually in isolation, but context changes everything. If a spike comes from a neuron that's highly trusted because it often signals relevant information and it arrives at the same time as others from similar contexts, the receiving neuron is more likely to fire. The synaptic strength, as in how strongly a connection influences the receiving neuron, also determines its impact. And this is where learning comes in. Over time, the brain strengthens or weakens connections based on which patterns lead to more useful outcomes. If certain combinations of inputs consistently lead to important things like recognizing your caregiver's face or detecting danger, then the neurons involved will become more tightly linked. This is how neurons that fire together, wire together, comes into play. And the result is that certain spike patterns become familiar to the brain. For example, when it sees something similar again, the same network fire. There is no need to interpret the signal afterwards. It's the pattern recognition that is the important part. The firing is the recognition itself. The brain state represents the object, the sound, the smell, or the thought. That it's the state of the brain that represents it. So in a mature brain, for example, when you see a cat, there is likely a relative consistent network of neurons that activate together when you see a cat. But that network wasn't hardcore when you, for example, at birth. We had to learn to see a cat over and over for the neurons to fire together such that the next time we saw the cat, we would recognize it because it was a learned phenomena that was slowly taught throughout our upbringing. The cat network in this example is formed by repeatedly seeing cats, hearing the word cat, or interacting with the cat itself. The visual system learned the pattern and the concept of a cat, which became an embedded neural activity within the brain. And so what this means is that the brain doesn't use translation, but uses transformation. Spikes are passed forward, combined, filtered, and re-weighted across many layers. Each stage builds a richer, more abstract representation of the world around us. And this is much like how artificial neural networks work and are built. There are simple features that get combined into complex ones. In fact, artificial neural networks were inspired by this very idea of how the brain works. In convolutional networks, CNNs, for example, early layers detect edges, mid-level layers detect shapes, and higher level networks detect objects. The idea of deep learning, for example, is based on this biological insight where complex meaning emerges from simple parts, combined and refined over many layers of neural networks. Neuromorphic computing goes one step further in that it tries to mimic not only the structure of the brain, but also the spike-based timing of the neurons within the brain. It captures the fact that the timing, that the synchronicity matters within the brain. One neuron might ignore a single spike, but it might fire if many spikes arrive together in a narrow time window. This sensitivity to coincide is fundamental to how the brain computes and processes information. So when we ask, how does the brain interpret a spike, we need to reframe that question in that one spike doesn't have a fixed meaning within the brain. Its importance depends on when it arrives, where it comes from, how strong it influences is, and what else is happening at the same time. It's always interpreted in the context of the neural network within the brain. Throughout our lifetime, this is what our brain does. It builds all these neural networks that gradually, through our learning, through the sensory input, they start firing together. They are wired together. They are fired together. That's essentially what the learning is. Through sensory input, trial and error, reinforcement, and social learning, the brain essentially shapes itself. The patterns that lead to useful outcomes are reinforced. Those that do not are tossed away. What remains is a brain whose very wiring is its understanding of the world. And that's the profound idea that our brain doesn't carry a map of the world. It actually becomes the map itself through the dynamic relationships of billions and billions of neurons within our brain. Spikes of the neurons of the brain are not messages with fixed meanings. They are participants in patterns that represent something only in the context of everything else that is firing around it. And that is why in neuromorphic computing, things become so much more exciting, because it shifts us away from the traditional computing where bits have fixed roles towards systems that, like our brain, compute through evolving dynamic representations and so forth. And if we want machines to think and perceive like us humans do, we must begin with this principle that intelligence is not built on decoding symbols. It emerges from patterns in a living network. And so if you're interested in getting into machine learning, deep learning, neuromorphic computing, and so forth, I highly recommend that you dig deeper into neuroscience, because the neural networks that have been designed for the past decades, as well as the ones that are upcoming, both within your traditional artificial neural networks, as well as the upcoming and future coming artificial neural networks, are all inspired by how the neurons and how the human brain works. And so the more you understand and start reading and educating yourself about neuroscience and the information and signal processing within the brain, the more equipped you will be once you start getting into the artificial neural networks field, because then you would be able to do that distinction and do that comparison, and hopefully it will also help you to even code better. So I hope this was helpful to you guys, and thanks again for watching and liking and commenting, and I'll see you next time. Bye.